Before the introduction to the real design for the most popular IP in analog IC design, that is data converter. Before the introduction to that, I would like to share the background about data converters because if you would like to do any kind of good enough design, you had to better fully understand what's going on with such kind of design. So allow me to help you do such kind of brain debugging, to debug what's wrong in your brains. Hopefully, I sincerely hope before your real design, you don't get any kind of misunderstanding about such kind of data converters. From the very beginning, I would like to say that nowadays, we hope to integrate everything on the same chip. So if you can, we will have the so-called system on a chip. 系统晶片. Just like what you have for your mobile phones. Nowadays, all the chips, actually, I mean the core chips for smartphone, they are some kind of system on chips. Just like Apple's right now maybe 14, okay, all those chips from Qualcomm, MediaTek, they try to integrate all the system blocks on the same chip. Actually, not exactly the same chip. Nowadays, they use 3D chips, okay, to integrate everything. Why would we like to do this? From the very beginning, we would like to focus on digital circuit first. Why? Because if possible, we would like to digitize almost everything. Why? Because digital signal is quite insensitive to noise. But why? Okay, they have only two states, just like this, only 0 and 1. During operation, it will be jammed by many kind of noises, interference. So finally, you will see something like this, right? Does it harmful? Usually not. Why? Because in digital circuit, they have the so-called threshold voltage. Yeah, we have also threshold voltage, but that is totally different. Usually, the threshold voltage for digital circuit is in the middle of your power rails. And it means 50% of the VDD. Above the threshold voltage, it will be always 1. Below it, it will be always 0. So in digital domain, we have the so-called data regeneration, 资料重生. Why? And what? Okay, if you have such kind of input noisy signal, then you can feed into any kind of digital gate. Practical instead of ideal. No, practical, good enough. Okay? So you have such kind of noisy input, and this is the so-called buffer, digital buffer. It means what? If input is 1, output will be 1. If input is 0, output is 0. That's it. Okay, that is so-called digital buffer. Anyway, what you can get? No worries. Here is below the threshold. So you will get 0 without any kind of noise. Okay? There, it is above the threshold. So no worries. You will get wow. So that is the definition for data regeneration. Okay. Inside the file, you can only get 0 and 1. You have no idea what's that. To enjoy it, you need the help of deck. To convert back the digital signal back to our analog domain. Then you can hear the audio signal, you can have a look at the video signal. And this is the reason why data converter is the most important IP on Earth. Even more important than ARM, okay? Because only with ARM, our smartphone doesn't work, okay? All your voice, all the images, videos, actually from analog domain. So before the smartphone can help you anything, we need ADC and DAC. Okay, that is really important for analog IC designers because for digital IC designers, they have no idea how to realize such kind of very complicated analog circuit. All right, even it is the interface between digital and analog. Sorry for that. Only us, only we can make it for humankind. All right, and in digital domain, everything, compared to analog, everything will become simple, easy to design, and it's reliable, and it can be scaled down very easily. Their gate tools are really mature, so they have automatic design. We don't, okay? And also you can get help from DSP, digital signal processing, to encrypt, 加密 your signal, or to compress, 压缩 your signal. We have a lot of issues to deal with DSP to enhance the performance or reduce the size of the content. Blah, blah, blah. And after that, you can use your microprocessor just like ARM, okay, or DSP logic to help you do everything you like. So it means what? We will get less pure analog chips. However, the same. Not only less pure analog chips, but also less pure digital chips. Most of the chips on Earth right now are mixed mode. It includes both digital and analog circuit inside. All right, let's go further. So why? We still need to have analog design, as I mentioned. All the signals in our real world, just like the audio and video, just like the flow, water flow, air pressure, temperature, everything is in analog instead of digital. Because they are continuous, just like the temperature, right? You don't have, something, right now it's 18. Moment later, it will become 19. No, sorry for that. No, okay? The change, the variation will be continuous. They are not discrete. So everything is analog in real world. Nothing is digital. Later I will show you the big difference between analog and digital signals. Anyway, as I mentioned, the core of everything of your computer, of your smartphone, even into the cloud, the core is in digital, but the real world is in analog. We need the interfacing circuit, ADC and DAC. And again, only analog IC designers can help humankind design those two. Okay? And how about the analog application? Well, a lot. Just read by yourself. So allow me to show you the major differences among analog and digital signals. From the very beginning, our signal is totally continuous. Okay, and theirs are discrete. 我们是连续的，他们是离散的。And what is the definition for being discrete? Okay, 单义对离离拉拉，就是这个意思。Okay, allow me to show you. Where is the signal there? Not here. Okay, anyway. I have no idea where are the waveform. Okay, allow me to show you. What is the definition for continuity? Okay, for continuity, for example, this is the time and that is the physical quantity you are interested. Usually, you guys interested in voltage or current, okay, right? So in analog, it means it is continuous. What is the definition for continuity? It means between any 2 points, there will be always infinite inside. Okay, 那个两点中间都会有无限多点。It means what? You have no way to figure out the 2 closest points. Sorry for that. Sorry, inside any 2, there will be infinite. That's it. Okay, that is the definition for continuity. If you ask me, that is in analog. And what is in digital? I mentioned already discrete, right? So what is the definition for discrete? Configurations. you can always find two closest points without anything inside. That's it. 你可以找到最近的两个点，中间没有任何东西。That is the definition for being discrete. Okay? So in this, that is totally different. In analog domain, everything is continuous, not only in time domain, but also in voltage or physical quantity domain. On the contrary, in digital domain, sorry for that, everything is discrete. Okay, just like this. It is not only discrete in time domain, but also in vertical domain, voltage or domain. Okay. Okay. It is not continuous. Nothing inside for time domain and analog domain. Okay, that is the definition. Voltage domain. That is the definition for discrete. Anyway, our design in analog domain needs to be customized. And it means you need to do everything by yourself. That's it. Alright? And how about digital design? Oh, they can be standardized. They have the so-called standard cells. 标准元件. Okay? So, according to standard cells, all the design can be standardized, can be automatic. Okay? And what do we need for model? Precise. Because we pay much attention to the accuracy. However, in digital domain, they don't touch any kind of precise model. Why? Many reasons. One of them is, as I mentioned, nowadays the chip contains more than tens of billions, 超过几百亿电晶体. So, for each transistor, if you would like to apply such kind of precise model, it is mission impossible, right? Even you use supercomputer to do any kind of simulation, I promise you, nobody can make it. No supercomputer can make it. Yeah. Sorry for that. Too much. Too complicated. So, in this way, they can only handle such kind of abstract model. However, they don't pay any attention to accuracy. Because, as I mentioned, they have such kind of big tolerance to any kind of noise or inaccuracy. I mean, error. Okay? So, they don't care. They are really lucky. And then, according to programmability, after fabrication, it is hard to change for our analog circuit. But how about digital circuit? It's okay because they have software or the so-called firmware. Okay, even after fabrication, they can change the code for software, firmware, blah blah blah. And for the design, we focus very much at circuit level, even device level, device, the transistors, blah blah blah. Okay. However, in digital domain, usually they only focus on system level. That's it. They don't have any kind of detailed thinking about how to implement it because EDA tools can help. And this means their CAD tools are really mature long time ago. Tens of years ago, all the EDA tools were mature already to help them to do automatic design. However, at our side, we are really unlucky. Yeah, because even till now, nothing can be automatic or handle design. You need to do it by yourself. That is really bad, but that is also good. Why? It means for all the IC design houses, they need a lot of analog IC designers to help them do all such dirty jobs. Okay? Because EDA tools cannot help. So according to the complexity, yeah, we need to consider a lot of parameters. And for them, usually they only pay attention to speed and power. Okay? So their design complexity is much less than us. I'm not talking about the number of transistors, no. I'm talking about how much consent you need to have. 你要关心哪些事？我们关心太多事了。So it means for future trend, again, less pure digital analog chip. Yeah, and we would like to integrate almost everything and low voltage or low power is the king. Okay, especially for analog design. For digital piece of cake. Low voltage, that is some kind of fundamental requirement according to the IC industry, the scaling down of the IC industry. Yeah, automatically they have such kind of low voltage design, right? And then low power design, again, according to scaling down, with the same circuit, digital circuit, for next generation, I promise you, they can run faster with less power. That's it. I mean, for digital IC designer, they simply enjoy the process evolution. We can't. Okay, we don't have such good way to enjoy it. We have a lot of dirty jobs to do. However, that is some of the key issues to ensure your future, because nobody can replace it. Okay, even EDA tools, no. Yeah. Anyway, anyhow, to your own goodness, I hope you can know both, not only analog but also digital, and then some kind of systematic view according to the application. It will help you to be promoted as managers, team leaders in the future. If you only focus on this or that solution, usually you cannot be the manager or any kind of team leaders. Then allow me to show you some more detail about the signals in time domain, analog or discrete. As I mentioned, everything is continuous in analog domain, but discrete in time domain. Here I would like to show you the process, how to digitize the analog signal and then convert it back. Okay. So from the very beginning, never mind your signal. Your analog signal is what? I mean, audio, video, temperature, air pressure, everything is continuous. Okay? Before ADC, you need to have that kind of low-pass filtering. Why? It is called anti-aliasing. I will have, maybe if I have time, I will have some more explanation about anti-aliasing. But you need to know some theoretical background, right? Anyway, in brief, what is that? According to the such kind of frequency band, okay, what you can process, I mean, what ADC can handle, can process, we just preserve it. And out of that, we need to remove it. Okay, otherwise, all those beyond the capability of ADC or before feedback to hurt what the ADC can handle. That is really bad. Okay? Since you can handle it, and all those you cannot handle will be feedback to hurt yourself. So we need to remove all those ADC cannot handle. That is the fundamental idea for anti-aliasing. I mentioned 4D back, right? That is called aliasing, right? And anti means to reverse it, to against it. I have no idea how to say this in Chinese because I never read it before. Just go on in Chinese. What is the meaning of that? Okay, anyway. After anti-aliasing, the first step we need to do is sample and hold. Because from the very beginning, that is continuous in time domain and voltage domain. Since after I only focus on voltage because you guys are much familiar with voltage signal. Okay? So, what is the function for sample and hold? Very simple. To make the signal discrete in time. That's it. Okay? So sample and hold, it means, in time domain, it is discrete. Okay? However, I need to warn you, after sampling, the magnitude is still continuous. Okay, because after sampling, what is the voltage of your samples? Or maybe you have 1.2, 3, 4, 5, 6, blah, 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 all the way to infinity. Okay, so in voltage domain, after sampling, it is still continuous. Okay, and how to make the voltage become discrete? We need the help of quantization here. Okay, so sampling is to make the signal in time domain discrete. Quantization is to make the signal in voltage domain discrete. That's it. Okay, two major steps. Why we need to make it discrete in time domain? Because if you don't do it, it is continuous in time domain. It means for each period, never mind how short the period you would like to process, you need infinite memory to keep the content. It doesn't make any sense, right? So we need to make it in time domain discrete. But since it's not so easy, after you make it discrete in time domain, it is still continuous in voltage domain. So again, for each sample, you still need infinite memory to keep it. It doesn't make any sense. So we need to make it also discrete. So we need the help of quantization. All right? And what is quantization? We have a lot of quantization levels. If you have n bits, then we totally have 2 to nth power, okay, quantization levels. And the definition for quantization in theory is to find the closest quantization level to your input sample. For example, here, right? They will say, oh, this quantization level is closest to the current sample. Then I use the number of the quantization level to present, to present the current sample. That's it. So from the bottom we have all zeros. For example, you have 3 bits, and then you have 0, 0, 1, 0, 1, 0, 0, 1, 1. Congratulations! This sample will be represented by 0, 1, 1. That's it. That is the very fundamental idea for quantization. Yeah, after sampling and quantization, congratulations, you get the so-called digital signal. After that, you can do everything you like. Okay, just like encryption, 加密, compression, 压缩, everything you like. Even you can apply the so-called digital filtering. Even in digital domain, we have many kinds of filters, and in theory, their performance can be better than analog ones, because in analog domain, nothing is perfect. However, in digital domain, everything is perfect. Supposed to be, okay? So the accuracy after digitization, you don't need to worry about the accuracy. It means, I always told you 1 plus 1 equals 2 definitely, right? In digital domain. But in analog, sorry for that, nothing. Perfect. Yeah. It never be 2.0000000 to infinity. Sorry for that. Don't be silly. Okay. That is the idea from the original analog signal to the represented digital signal, or we call it digital code. However, you don't have any way to enjoy it, as I mentioned. Never mind, this is audio, video, or any kind of signal. Not only for humankind, but also for your pets, for your dogs, for your cats. Sorry for that. Nobody, no animal can enjoy any kind of digital code. If we would like to enjoy the content, we need to convert it back. So that is the responsibility for that. Digital to analog converter. Yeah, and reversely, we need to make everything discrete to become continuous. That's it. So after conversion, you will have such kind of stairwise 阶梯状 stairwise signal, right? Are you happy with that? No. It is not the same with the original one. So you need another low-pass filter, yeah, to smooth such kind of stepwise signal become very smooth. That's it. Okay, and hopefully the output signal will be exactly the same as the original one. Is it possible? Oh, sorry for that. Nothing is perfect. There is always some error. So our responsibility, I mean this is for analog IC designers, because for everything here is supposed to be ideal. If there's anything wrong between this and that, then more than often you will be blamed. You don't do a good design for your ADC or your dad, you need to redesign all those. That's it. Okay, yeah, so analog and digital signal, right? Everything is continuous in analog. All right, here I would like to show you, for example, this is your original analog signal. You may be curious, as I mentioned, because our capacity for memory is limited. We need to do sampling, right? But how many samples you need to get from the original signal? So I'm talking about the sampling rate. How much sampling rate you need to have for any kind of signal? Okay, I think most of the students here already know the result. From theory, it is the so-called Nyquist rate. Okay, however, why? Oh, please go back to read all those theories, maybe for linear system, signal processing, or telecommunication. I don't care, don't mind, okay? To be a good teacher, I would like to explain how much you need, okay? I wouldn't like to waste your time and my time. I don't have time to. I'm not the teacher for your DSP or your linear system. So, the most I got from myself is explanation. And how much? Allow me to show you. Is it okay? The blue dots. Here, 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 and there. Are they good enough to represent the original one? Wrong, right? Because I mentioned already, after sampling, quantization, if you want to enjoy it, yeah, you need the help of not only that, but also low-pass filtering, okay? Low-pass filtering. So what does it mean? If you have only such kind of, only such kind of sample, then after low-pass filtering, I promise you, the output will look like that. They are not the same, okay? Because you will lose all the small variations. Okay. I'm talking about the high frequency components will be missed. Only the low frequency component can be represented. Alright. So the hardest part, the most difficult part is to represent all those the highest frequency component. Right? Right? So how to represent such kind of very high frequency, the highest frequency component? Very simple. Very simple. In idea, you can have a sample here, 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 right? Right? That is the best. Right? But what does it mean? Because it means for the highest frequency, according to Fourier transform, or you had better learn something about Fourier transform. Okay? Fourier transform will tell you for any kind of analog signal, it will be represented as the combination or integration of many kind of sine waves from low frequency to high frequency. That is the most fundamental idea for Fourier transform. Yeah, that is what the best for you to learn. To make your background much more solid than before. okay, for such kind of discretization, quantization, sampling, blah, blah, blah. In NTU, yeah, 10 years ago, I took the class called Fourier transform for 1 semester, okay? That is some kind of graduate class, for one semester. Then you can fully understand the operation principle, all the ideas according to the principle. Anyway, that is too much for you. All right, I wouldn't like to take any class like this. After that, you can do analog IC design. It doesn't make any sense. 2 time wasted. Okay, allow me to show you the most fundamental idea. For the highest frequency to fully represent it, just like this. Okay, so what is the fundamental idea? For each period, you need 2 samples. Got it? Okay, that's it. You don't need to take any class related to Fourier transform, linear system. No. That is the best I can do. Keep this in mind. For the highest frequency, each period, you need 2 samples in theory for the best representation. Right? So if the highest signal is this, so it means what? 2 times higher than your highest frequency, right? That is the definition for Nyquist already. Okay? Yeah, anyway. So, but in theory, if you are lucky for the highest signal, if you are lucky here and there, right? If you are unlucky here and there, oh, sorry for that, you will still get 0. Keep this in mind, okay? Even you follow the recommendation or Nyquist rate in theory, there will still some chance to make this one wrong. So it is required more than, instead of equal to, larger than, 2 times higher than your highest frequency. Okay, that's it. So on the contrary, if you tell me, oh, right now my sampling frequency, right? So you can see on the contrary, right? The signal frequency can only be less than instead of equal to no. 50% of the sampling frequency. So if you tell me, right now my ADC operate at 10 kilohertz, right? How about your input signal frequency? The highest should be less than 5. Got it? And for our voice, human voice, the highest for tenor, soprano, sorry for that. The highest pitch from the lady. Oh, okay, that's it. Okay, how much? Okay. So it means to record, to digitize our human voice, we need 8 kilohertz at least. Okay. However, if you are talking about music, how good human ears can hear? 20 kilohertz. So it means what? For sampling frequency, at least 2 times higher, right? So 40 kilohertz, right? If you have a look at the original specification for CD, right now that is after that DVD and that blue disc and that no limitation because everything is put online, right? But from the very beginning, Philips as the most famous director for foreign harmonics orchestra or anything, yeah, Hawaiian or something. Okay, yeah, they actually from Mr. Kaoyang, how much sample? Oh, it is decided by the engineers from Philips. However, how long each CD can hold? The record them the longest. How can I say? Yeah, the longest thing is around something from better, but anyway, after the time is some kind of slow director, and everything is slower, a little bit slower than the others. So the total length is around a little bit more than 60 minutes. Okay, so finally the definition is 44.1 kilohertz, because larger than that. And for each disk to hold the longest one, okay, more than 60. So totally, to my memory, maybe 70 minutes. That is from the very beginning, some kind of milestone for humankind's digitization. Until now, if you have a look at the content of my video clips, you will see what is said by student, the TA, how much sampling rate, for how many bits, blah, blah, blah. Actually, if you go back to the origin, that is what I would like to share. Okay? Till now, CD audio means stereo, left and right, and 44.1 kilohertz. How many bits? For high-end audios, I guess more than 20 bits will be best. In the past, maybe 18 bits. But right now, according to some kind of delta sigma data converter, it is pushed higher than 18. So at least 20 bits, even for your mobile phone. 20 bits means almost mission impossible for traditional ADC or DEC design. We need some kind of innovative structures for that. Okay. Yeah. Fine, let's go ahead. I waste too much time. Oh, just like this. Okay. It looks maybe good enough to represent the finest feature, 最精细的那个最细微的表现。Two times, at least 2 times for the highest pitch. Okay, highest frequency. Yeah. Anyway, anyhow, as I mentioned, in digital domain, everything can be flexible. It is easier to be upgraded. You don't need to worry about the accuracy, and it can be reproduced as many times as possible as you like. You don't care, but yeah, that is good. But on the contrary, it has also a lot of limitations. Okay, allow me to show you. To make the concept even more solid, I would like to show you the typical audio system, just like you would like to call your friend, your family through your mobile phone, right? So from the very beginning, you need to talk, not to your friends, you talk to your phone, right? Before your voice, your sound reach your phone, it is analog, all right? Why you can hear me? According to my voice, my cord, to vibrate the air. So the air pressure in this way will be transmitted to all your ears. All right, and such kind of air pressure can be listened by your ears. Okay. So from the very beginning, we have such kind of voice or music or speech. According to the variation of air pressure, and then we need something to convert such kind of physical quantity into electric signal. Otherwise, our circuit cannot handle it. Our circuit cannot handle the air pressure directly. No. So before our circuit, 电路 can do something. All the signal needs to be electrical. Okay. So we need something called sensor. What is the definition for sensor? To convert the signal from one physical quantity domain to the other. 它的定义就是把讯号从一个物理量转到另外一个物理量。That's it. Okay? Yeah, so right now we would like to transform the air pressure into electrical signal, voltage or current, I don't care. Yeah, such kind of sensor, usually we call it microphone. Okay, through the help of microphone, we'll get the electrical signal, just like voltage, for example. And then we can do digitization. And after that, you need to, again, to encrypt it, because you wouldn't like the others to listen to what you are talking about through the phone, right? We need to encryption, jamming, compression, because the channel in the air is really expensive. Our companies pay a lot of money to the government to buy the bandwidth from the air. It's really expensive, so they would like to compress your signal as much as possible to save the cost. Anyway, after any kind of digital processing, we can transmit the signal to the air and then receive at the other side your friend or family you called. Okay? Yeah, but again, that is fully in digital domain. They cannot enjoy your voice or even your image, right? We need the help of that to convert it back to electrical signal, and then we call it actuator. Okay? Yeah. 启动器或啥东东 actuator. Actuator. Okay? Hopefully the spelling is totally correct. Hopefully. Anyway, to convert the electric signal back to air pressure for you to listen, then such kind of actuator usually call it speaker. Okay? And then that is the voice, music, or speech your friend, family called by you. If we would like to sense the quality, then you can compare the final one to the original one to see how much difference, to check the quality, right? To make it perfect, it means, oh, the difference is 0. Oh, sorry for that, nothing is perfect. So in the past, one of the professors in Taiwan, how can I say, he applied some kind of project from Ministry of Science and Technology. He bought a car to install all the equipment inside the car, right? To help all the companies, 中华电信、大哥大、美传 all of them, to sense the system quality. So, after that, what he needs to, what his students need to do. Drive the car, for example, this is Taipei City, right? Drive the car all the way, right? And then you get a lot of money from the first company, Zhonghua Telecom. And after that, get another big money from the others, right? To do the same dirty jobs. Wow, since after the professor got a lot of money. Also the student, but maybe 90% to the professor. And the student, the graduate, only drove the car to sense everything. Okay? They only then repeat the report. How much difference to the telecom company? And they need to fine tune the base station, blah, blah, blah. Okay? Or the antenna. Wow. If you are a money lover, don't do any of the design. Just to set up the environment and get money from the telecom company. Yeah. Anyway, that is only a joke because it's already done. What is done is done. Only for 5G. They still need somebody to do some kind of CE job. However, I guess they have their own team to do it. Okay? That is the case. Okay. Let's have again, just took your mobile phone as a very good example. Everything you would, just like you would like to knight somebody or to send a message through messenger, I don't care, or photo or video, I don't care. The information actually is digital, right? How can you transmit such kind of digital, that is transmitter, right? How can you transmit such kind of digital information into the air? Sorry, in the air, everything should be in analog. Okay, you cannot transmit digital waveform just like this. Sorry, the telecom company will kill you, or the government will kill you, because if you transmit anything like this, according to Taylor series expansion, Taylor 展开式, right? If it is 1 gigahertz, then all the harmonics, 2 giga, 3 giga, 4 giga, all the way, will also exist in the air. You will interfere all the other radio stations, all the other companies. It doesn't make any sense. Alright, so anything you would like to transmit wirelessly, it should look like this, sine wave, very pure sine wave. Okay. Only with sine wave, you can have the so-called night spectrum. Okay, only one night in theory. Okay? But you need to do modulation because you don't transmit the pure sine wave to the other. If so, for the receiver, they can generate the sine wave by themselves, right? They don't need your help. So the information is modulated into such kind of carrier, the sine wave, with phase modulation, magnitude, anyway, okay? That is the definition for digital communication, but keep this in mind. What does it mean for digital communication? It only means the content is digital. Don't think, oh, the signal is digital. Oh, sorry for that. Digital signal can only be transmitted through wires, cables, okay, fibers. It's okay with digital signal, but sorry for that. In the air, nothing can be digital. Okay, that's it. Yeah. So according to modulation, actually, the night spectrum will be melting. Okay, it will look like this. All right. So we have the first band, the first carrier, the second carrier, the third carrier. Everybody like this. Okay. Then in between, we need to have the so-called guard band. 护卫带. Okay. To prevent, to keep away the how can I say, the spectrums, okay? Yeah. And then at the receiver side, they need to have very good bandpass filter to filter out the band they needed and reject all the others. Got it? What I'm talking about needs to be done in analog domain instead of digital. Nothing is for digital IC designers. Okay. Anyway, anyhow, this is the digital content we would like to transmit into the air. And again, it is really expensive to transmit signal wirelessly. So you can see we have I data and Q data. What does it mean? I means in phase. Q data means out of phase. And the difference is 90 degrees, sine and cosine. Okay? So you have, sine by sine, you will get something out, something. Okay? Cosine by cosine, you will get something. However, cosine by sine, you get nothing. Got it? I think you learn such kind of very simple mathematics from your senior high school. Okay, that's it. So you can see, for example, I for cosine, then Q for sine. What does it mean? With the same frequency, we can transmit two data at the same time. Okay? Yeah, so the transmission rate, bit per second, is double by such kind of idea. Wow! It double our, not the bandwidth, no. With the same bandwidth, the content can be doubled for transmission. Wow! That is another milestone for telecommunication. Okay, anyway. But how to generate the sine and cosine? Oh, we have the so-called local oscillator. Okay, yeah. For FM radio, according to American FCC's regulation, this is so-called baseband. Baseband is what you can listen to. You can listen to, you can watch. Okay. For audio, I told you already, the maximum is 20 kilohertz. And how about video? 6 mega. Okay. That's it. That is so-called baseband. And modulation is to shift the signal from baseband to higher frequency band. For what? To get less attenuation. If you have a look at our air on Earth, 大气, our atmosphere, you will see the attenuation. Okay. So we would like to shift. This is the baseband around DC and 2 gigahertz, right? You would like to move the signal from the baseband to the other band. I don't care which band. But the major purpose is to reduce the attenuation very, very much. That's it. If you don't do such kind of modulation, sorry, if you say, hey, somebody, okay, out of the classroom, nobody can hear my voice. Yeah. That is some kind of our mother nature is designed. I don't care by anybody or nobody to protect all the animals on Earth. Even for Taiwan, right? If a tiger in the middle, Yushan or Alishan, okay, he roar. Wow. He made the loudest voice that all the mother tiger will reach the guy. Oh, that is the most powerful one. I promise you, all the animals will be distinguished according to DNA, right? Too close in DNA is no good for animal or humankind. So the truth is, without any modulation, the baseband transmission get the highest attenuation. So the voice, never mind for humankind or for animals, cannot be transmitted too far away. So even in Taiwan, or you have a tiger here, tiger there, oh, they have their own territory. They can roar to call their wife within some limits. Okay, the most I guess kilometers within that, not much more than that. How about whales? They also need to attenuate, to modulate their sound to very low frequency because that is the good way to be transmitted inside the sea. Okay? So the frequency becomes very low for whales, dolphins. That's it. Especially for whales because they need to call their wife or husband maybe tens of kilometers away. Okay, that's it. Otherwise, they cannot find anybody to mate because they can swim from the south to the north and then back to the south. Who knows where they are? That's it. Okay. Anyhow. Oh, all right. I am not your telecommunication teacher. Anyway, we need to modulate the baseband signal to your radio frequency, okay, to the high band, to the high band. For FM, from baseband to midband, how much is midband? 10.7, and then all the way to the radio band. Okay, that's it. For FM, around 88 to 108 megahertz. All right. In this way, the radio wave can be transmitted far, far away. When I was young, I lived at the top of second dormitory. When I was single, so I played some kind of city band. Okay, yeah, with only 5 watts. But how about the antenna? I just get some kind of wire. Okay, then I cut it according to maybe 1/4 wavelength because the frequency is around 27 megahertz. According to lambda, right? How much lambda? I have no idea. I have only some kind of dipole. I wouldn't like to spend any money on that. So I go to the warehouse of our department to get the wire, then cut it according to 1/4 or 1/2. Alright? Then put on the top of the dormitory. And then I call my friend. how long? The northeast actually some kind of fish boat. Somebody on the fish boat. I call it, and the boat actually was from South Korea. Oh, 5 watts. Okay, only. And what is the southeast? I call somebody. Live very close to Manila, in Philippines. 5 watts. Single. With only 5 watts, I promise you, from here to the main door, okay, nobody can hear you. 5 watts only, too small. Okay, anyway, anyhow, that is the power of modulation. Yeah. From baseband all the way to 27 megahertz, 5 watts can reach South Korea and Philippines. Bingo. Okay. Yeah, then we call it local. Why we call it local? Local means here. Alright? And what is non-local? Base station. You have some kind of base station. You need to transmit your local signal all the way to the base station and then back to another local signal of your friends or family called by you. Anyway, anyhow, that is the idea. Okay? So, from the beginning, we need cosine and the sine, then sum them up with the help of modulator to from baseband to midband, and another mixer from midband to the final frequency you like to have. And then power amplifier to drive the antenna out. Then at the receiver side, the same RF signal will be received from your antenna. How much is the magnitude? Only microwatt. Only microvolt, sorry. Okay? So in this part, some kind of filtering image rejection flow. I wouldn't like to teach you anything like that. Too much. Okay? Then we need the help of local of LNA and convert the radio signal to midband and then to baseband. Reverse it. Yeah. Oh, before that, how can you convert the digital to analog? We need D to A, right? That. And at the receiver side, A to D, so we need ABC. Then combine I and D to get to recover the final digital content for the friend or family called by you. This is some kind of quality check. Yeah, the layout and then the micro photo, and you can see tag AD, and then and other. The second important ID on Earth is lock loop. Lock the loop. Okay? So not only data converters, the most important one, and then locked loop. It includes PLL and DLL. First locked loop, delay locked loop, yeah. Or even for software radio, everything can be coded. But you still need help of ADC, that, blah, 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 all of them. Right? So if you want to digitize everything, it means that ADC and DAC needs to operate at very high frequency, just like gigahertz. Is it possible? Maybe, okay. Yeah, nowadays we have some ADC can operate at very high frequency. However, the cost is really, really high. Alright? Yeah. And even for motor control, just like Tesla, right? Tesla needs to control the motors to drive the motor at what kind of speed the driver would like to have, blah, blah, blah. How to control the speed of the motor. Oh, you need. That is what I get from analog device, in brief ADI. Okay, it needs a lot of data converters. Yeah. That. Okay, AD something from analog device. Yeah, that's it. Not only for the cars, for your smartphone, everything. Nowadays, all the consumer electronics, I promise you, they contain ADC or DAC. Alright, if you take away the data converter out, nothing can work for you. Then you need to go back to the future. Yeah, just live in Stone Age. Okay. Oh, that's really bad. Now let's go further for, that is some kind of brief introduction. Then, for the data converter background, again, I got the help from Randall Geiger, yeah, from Iowa State University. That is our tradition to say thank you to somebody. Worship. Yeah, he's not, he's still alive, very healthy. Okay. Anyway, you guys had better thank Professor Geiger's contribution, because since after most of the material is provided by Professor Geiger, I simply copy and paste. But I got the permission from Professor Geiger already. Yeah. When? Again, maybe a little bit later than 2005. Okay? Maybe 7 or 9. In the past, I invited Professor Geiger to visit NTUST once for 2 years. Yeah, but after some time, he became older and older, right? Yeah, even maybe 2 years ago, I invited him. He said yes, but we never made it. Anyway, let's wait and see. Maybe after the pandemic, I would also like to invite him again. Yeah, to show him my students. Nowadays, my students are much better than before. Okay. Anyway, through his help, actually, we signed a very good deal for student exchange between NTUST and ISU, Iowa State University. Okay, let's have a very brief break. Then we will go through as fast as possible. All right, that is only the background. We never touched the real design until now. Okay, so hopefully I can finish it very soon. Then we can go for the data converter design.